Good morning. Today, I'd like to talk about a minor variation on a theme of the disk method called the Warscher method. In the disk method, we calculate the volume of a small disk as being pi times its radius squared multiplied by the perpendicular height. In the Warscher method, we're going to think about a situation where you have a disk, but someone has taken a Dremel tool or something like that and drilled a circular hole right down the middle of it. I've drawn the axis of symmetry of the thing in an effort to show that those circles are supposed to have the same sort of centers to them. The situation is now more complicated. I still have a perpendicular distance as before, but now there are two radii involved. I can calculate the volume of the shape that I get by removing the middle piece, by calculating the volume of the regular disk of radius, big radius, and subtracting away the volume of the small disk. Of course, both of those terms have a factor of pi, so I can factor that out. Both also have a factor of a perpendicular height. All that will remain after I factor that out is the square of the big radius minus the square of the small radius. This is going to be our recipe for how to calculate the volume of a washer. I want to look at a few examples of this kind of thing. I want to think of taking the region in the first quadrant below the graph of y equal 2 minus x and revolving that around the vertical line where x is equal to 3. Up to my terrible drawing abilities, this is going to be a shape that's flat across the bottom, flat along this edge, and on the inner edge, it's going to be slanted, like this. Since I'm revolving around an axis that is parallel to the y-axis, what we'll do is we'll use the y-axis as a ruler. We'll split the range of y numbers up into smaller pieces. If I shade in a couple of the relevant rectangles, those are the kind of things that I'm going to revolve around the line x equal 3. For instance, if you think of this one, every point in this horizontal strip is going to get revolved around x equal 3. These points are not important to me. They're not included within the region that I'm going to revolve. I have to identify the big radius and the small radius. The big radius is as far as I can get from the axis of rotation within that one strip. Let me draw this strip in separately. I'm going to measure the horizontal distance using the x-axis as a ruler. The good news is, if I'm as far away from the axis of rotation as I can ever get, I'm on the y-axis, regardless of which one of these strips that I'm looking at. On the other hand, as I let the y vary, the right end of this interval is going to vary. So I'm going to have to think about this sort of carefully. It's probably best to actually say it in words. the right end of this horizontal strip is going to have x-coordinate that is the x-coordinate on the graph of y equal 2 minus x that goes with y equal ci. For this particular setup, that's not going to be very difficult to figure out. Just doing a little bit of algebra tells me that the x, the right-hand end of this strip, is located at 2 minus c number I, where c number I is the representative y number within chunk number I. We want to be real clear about something, though. Neither one of these numbers necessarily are the radii that we're interested in. Let me draw the picture again. If this were just the disk method, if I were including all of this, then the radius would be the horizontal distance between x equals 3 and x equals 0, and life would be easy. Here, though, the horizontal distance between x equals 3 and x equals 0 is going to be the big radius. But I have to account for the piece that I have drilled out. I don't want to include places where x is between 2 minus ci and x equals 3. Using our ideas about the length of an interval being the rightmost number minus the leftmost number, the small radius must be 3 minus the quantity 2 minus c number I, which reduces to 1 plus ci. So we now know what the big radius and what the small radius is. We can write down our recipe. The recipe was pi multiplied by big radius squared minus small radius squared multiplied by perpendicular height. I can just write that down, though, since we know what the big radius, the small radius, and the perpendicular height are, and by now it should come as no surprise to you that we're going to add up all such things and take the limit as all of the delta y numbers go to 0. Don't forget here, c number I is a y number, not an x number. To finish the setup of the problem, all we have to do is to put in the limits of integration. That'll be the biggest and smallest relevant y values. In our description of the problem, the y value could be as small as 0 or as big as 2. This completes the setup. The volume that we're trying to calculate is the value of this integral. That integral, though, is going to be easy to calculate because it's just a polynomial in terms of y. This second term is 0, so I'll ignore it. And assuming that I've had enough caffeine this morning, this reduces down to 28 pi over 3 units of volume. As another example, a much more horrible example, I'm going to think about the graph of y equal x times 2 minus x. This is a downward opening parabola. The y-coordinate is obviously 0 when x is 0 or when x is 2. I want to take that shape and revolve it about the vertical line x equal 5. This is going to be worse than the other one because when I'm looking at the big radius, I'm not always going to go all the way to the y-axis. Things are going to be more complicated. As before, I'm going to chop the range of y values up into smaller pieces. I'll call one of them delta y, number I. Within that chunk, I'll select y equals ci, and I'm going to think about what I get when I revolve this picture about the vertical line x equal 5. Firstly, none of these points matter to me. None of these points are points of the region that I'm interested in. Also, none of these points matter to me either. They're not within the region that I'm revolving. The thing that I'm interested in is this. If I revolve that about x equal 5, I'm going to get a washer, except this time neither of the radii are going to be constants. Let me draw a magnified picture of this. I need to know the coordinates that I've indicated by question mark and 2 question marks. I want to be as absolutely transparently obvious as I can manage here. If you tell me y equals ci, there's going to be 2 points on the graph of this parabola to go with it. The left end and the right end. This x number, question mark, is going to be the smaller of the 2 x numbers on the graph y equal x times 2 minus x that goes with y equals ci, whereas this x coordinate is the bigger x number that goes with that same graph at y equals ci. So I'm going to need to know the x numbers in terms of the y numbers in order to know the x coordinate of that spot and the x coordinate of that spot. If you rearrange that, though, if y is supposed to be x times 2 minus x, and also we know that y is equal to ci, that turns the situation into a quadratic equation for the x's that I can figure out in terms of the ci numbers. So finally, I have formulas for the left end x and the right end x that go with y equals c number I. But there's more to it than that. These numbers themselves are neither the big radius nor the small radius. Let's draw a picture again. We're revolving around the vertical line where x is equal to 5, so let's draw that in. The big radius is going to be from the axis of rotation to as far away from the axis of rotation that I can get, namely x equal 1 minus square root of 1 minus ci. The small radius is the horizontal distance from x equal 5 to as close to x equal 5 as I can get in this strip. That'll be x coordinate 1 plus radical 1 minus ci. Remembering our business about upper minus lower and rightmost versus leftmost, we can now write down formulas for the big radius and the small radius. So to finish setting my integral up, I need to do this. I need to square this quantity, subtract away the square of that quantity, multiply the result by pi, multiply that by delta y number I, add them up, and take the limit. As usual, this is going to turn into an integral. Not to belabor the point, but c number I is a y number, not an x number. And consulting the picture that we drew at the beginning, the y numbers can be as small as 0 or as big as 1. The volume that I'm interested in calculating is this awful looking thing. It turns out that the algebra will simplify some for us, so this isn't really as bad as it looks. If I use well-known properties of algebra, I can expand the square of a sum and the square of a difference easily enough. I'm being very careful about grouping symbols here. I don't want to get a sign wrong. 16 minus 16 cancels out. 1 minus y minus 1 minus y cancels out. I've got 8 radical 1 minus y. I've got 8 radical 1 minus y minus the negative of 8 radical 1 minus y. To finish this, I just need to figure out the integral from 0 to 1 radical 1 minus y dy. There's at least a couple of different ways I could do this. One would be to just do a u substitution to get an antiderivative, express that back in terms of the original y, and then put y equals 0 and y equal 1 into it. Another way would be to do a u substitution again, but this time make everything in terms of u, and then do it that way. For variety, I'll do it that second way. If we can evaluate this integral, then we'll just multiply it by 16 times pi and have our answer. I think we've seen an example of this kind of thing before, where I pulled the factor of -1 out front and used it to interchange the limits of integration. I claimed at the time, though, it didn't make any difference, so this time I'll just leave things the way they are and then see what happens. There's no problem doing the integral. The volume comes up 16 pi times the value of this integral, which was 2/3. The volume is 32 pi over 3. Doing the volume with the Warscher method, in this case, was completely doable, but it was a horrific mess. In an upcoming video, we're going to see another method called the shell method, in which this particular problem becomes very easy to do. Until then, I hope everybody has a good day, and I'll talk to you again soon.